I'm gonna go. Okay. Hi, everyone. So today we have with us Daniel Whiteson, as physics professor at UC Irvine. He's also a co-host of a podcast called The Extraordinary Universe. He also co-wrote two popular science books and co-created an educational preschool television that is available on PBS. So we're all super excited having here Daniel with us today. He mainly work on machine learning and statistical tools to analyze energy physics data from the collider experience. And today he's going to talk about learning to find weird tracks. So please, Daniel, take it on.
Great. Thanks very much. Really appreciate it. Thanks for the invitation to escape Southern California in February and enjoy the weather here in Boston. Appreciate it. So today, yes, I'm going to be talking about how we can learn to find weird tracks. And yes, I will be defining weird at one point. I wanted to start by introducing myself because my research program is kind of broad, and today I'm going to be talking about just one slice of it. And since not everybody here knows me, I'm just going to briefly tell you about what I do more broadly. So my day job is I'm an ATLAS experimentalist, so collider physics, using precision measurements with high fidelity machine learning, for example, and looking for displaced tracks. And I work on the trigger. This is my postdoc Oishik, who's an expert in simulation-based inference, and my student Kevin, who does unfolding, for example. I also, of course, work on machine learning, which is why I'm here. Recent papers include work on approximate symmetries or machine learning tracking. That's what I'll be talking about today. Fast simulation and jet parton matching. I do a little bit of astro. So, for example, papers on neutron stars, and I have a project to use smartphones to build a massive planet-wide cosmic ray detector. And also some work in theory using, for example, machine learning and reinforcement learning to explore high-dimensional theory spaces. We had some discussions this afternoon, and also generating novel theories with machine learning. And then I also do some science communication, which I'm going to be talking about at the end of the talk. So let's talk about learning to find weird tracks. The motivation here is to try to use machine learning to do more than we normally do. Like, machine learning has been very powerful and very effective, but the story is basically, let's find ways that we have taken shortcuts because problems were intractable, and go back and do those things correctly with machine learning, or more effectively with machine learning, to squeeze out a little bit more power. So machine learning has been excellent at finding those places in our pipeline where we took shortcuts, replacing those heuristics with something more effective. And for example, Oishik uses machine learning to do simulation-based inference. We can actually take advantage of the quantum interference terms. And Jesse and Ben and other folks developed very powerful unfolding techniques using machine learning, for example. So allowing us to do things in higher dimensions to capture the wonderfulness of our data. And that's all great, but that's not what I'm talking about today, because what I want to do is something more. I'm hoping the machine learning, with its incredible capabilities, can let us break down walls to make new kinds of discoveries. I'm interested in places where we've walled things off and said, you know what, that's impossible, so we're not even going to try it. But now these new tools might give us a way to knock down old walls and say, hey, that problem, which we always thought was totally impossible, so nobody even thinks about it anymore, maybe now it's actually possible. Let's try it again. So that's what I'm going for with machine learning. That's what I'm hoping for. And one thing that strikes me, this is how I got into tracking, is that a lot of the discoveries we've been making recently they're wonderful, but they're somehow less satisfying, less dramatic than some of the discoveries in the old days of particle physics, right? Like, here you have the positron discovery, right? One particle, one Nobel Prize. It's a pretty good ratio, right? Right? Here's a muon, and you can put it in your paper and you're like, here's my muon, right? That's cool. And the reason is these are low rate, but they're background free. Okay, and so a lot of that's been done already, right? The background free stuff, the high rate stuff has been done. And so now we need to do physics, right, with large backgrounds that we manage, and all of our results are statistical. And along the way, we had to change how we did tracking. Instead of having folks look by hand at how tracks are and follow them using your own mental neural net to find these tracks, we had to do this at a very high rate, because now we're looking for subtle signals now, right? So we need to digitize it. And so we have computational scanning and digitized data, but computational tracking at high rate comes at a cost because tracking is hard, right? Precisely stated, you start with a set of hits, places where your particle has interacted with your detector, and you're looking to reconstruct the trajectory of some particle that went through. But of course, not all the hits come from your particle, and there are many particles, and there's noise, et cetera. So it's a huge combinatorial challenge to even consider all the possible sets of hits which might make a particle track. So fast tracking in principle is not hard, right? Just set a loop, consider all of them, you're done. But fast tracking is hard because of this combinatorial explosion in the number of hits that you have to consider. Okay, so tracking is a hard problem. We have smart people. They made it simpler. They said, well, we don't need to consider every possible set of hits. Let's consider only the kind of hits we typically see. So, for example, most of the particles begin at the vertex, right? You have this tracking volume. Do you really need to look for a track that starts here and goes over there? No, the tracks come from the same place. So why don't you build your tracking algorithm to look for tracks that come from where you know the tracks are coming from, right? Very obvious and huge speed up because it reduces the number of tracks you have to consider. Another assumption is, well, we either have neutral particles, which we can't see, or charged particles, which move as helices in a constant magnetic field. So let's look for helical tracks, right? So two huge assumptions, which make the problem a lot simpler, but also crucially limit what we can discover. Because if we're not looking for tracks that don't come from the vertex, or we're not looking for non-helical tracks, we can't find them. Now, there's been the recognition in the last 10 or 20 years that looking for tracks that don't come from the vertex is worthwhile. It's hard, but it's very worthwhile. And there's now a very robust physics program, right? Displaced vertex, displaced jets, disappearing tracks, appearing tracks, all sorts of stuff. Each of these requires a dedicated effort to develop a new tracker, which is good at this, and they're expensive, totally worth it. I'm not going to be talking about this because I think this is already well explored. What hasn't been very well explored, in my opinion, is the question of helical tracks, assuming the tracks are helices and closing our minds and our eyes and the discovery potential to things that are not helices. And one reason is that it's hard to let go of this assumption. The way a lot of tracking works is you start with some small set of hits. You don't just consider all the hits. You start with a set of hits. And you say, well, I'm going to fit this and get some tentative parameters. And then I'm going to extrapolate those parameters and, within some uncertainties, consider hits within that window. This strategy, Kalman filtering, lets you, for example, consider only a subset of the hits to add to your track, not all of them. So again, vastly reducing the space you need to consider. But this requires you to have in advance a parametric form for your track and to assume what that form is. So traditionally, we do track finding and track fitting simultaneously to simplify the problem. So the helical assumption is very, very deeply ingrained in most of these traditional track finding algorithms. What about finding non-helical tracks? Could you just take this same algorithm and replace it? Matt comes up with a new particle and it's not a helix, but it's a schmelix or whatever. You have some new parametric form. Can't you just plug that in and run your schmelical track finder? Sure, but then you have to specify that new parametric function, right? Wouldn't it be awesome if instead we could find tracks that we didn't anticipate? If there was something weird in our data and we could run a tracking algorithm that found it without us having a parametric description of it in advance. That would be really fun. And as far as I know, this is an open problem, right? So I'm going to go into a couple of specific details in a minute. The name for them is almost as silly as Schmelix particles. But this to me is an open problem. It means that we basically don't know how to look for these particles in our data. And we have a lot of data. And as far as I know, we haven't looked at it, which means in our data could be waiting for us some like very cool track, which if you looked at, you'd be like, okay, look, that's something. Like, I don't know what it is, but that's something. But we currently don't know how to look for it, right? It means it could be waiting there for us, ready to be discovered, but somebody needs to write the algorithm to pull this thing out of our data. And currently, our algorithms are blind to it, right? And so I don't know why you got into particle physics, but I got into particle physics for moments like this, right? Not to push the limits on the squiggly on mass by 10 MeV, but to change the way we think about the universe and to make crazy discoveries. And so, I want to see if there's a possibility to use machine learning to find tracks that we cannot anticipate, to make what used to be possible, single event discoveries, possible again. Okay, so fortunately, other folks have been working on machine learning tracking for other reasons. So GNN-based tracking, the ExaTrack project at Berkeley and other places, was developed in order to handle high pileup environments. So you got all sorts of noise from other tracks. Tracking gets more complicated as you get all these noisy tracks. Turns out GNNs do better. They perform better at high pileup than traditional tracking. Really awesome. With a side benefit that the GNN separates track finding and track fitting. So traditional algorithm, fitting and finding at the same time, here finds the tracks as a set of hits and then later fits them to a helix, which gives us the possibility of training it to find other kinds of tracks, right? This has nowhere in the track finding is it assuming a helix at all. You just teach it. Here's a bunch of helices, find more like this. So if we can train it to find something else, then maybe we can train it to find new weird stuff. So this is the question. Can we train a machine learning tracker to find weird tracks? I have not yet defined what weird is, but now I'm ready to answer Matt's question and start with finding one specific example of non-helical tracks, schmelicals, tracks, or whatever. Then I'll define what I mean by weird tracks more generally. And then I'll talk about anomaly detection for weird tracks. At the very end, I'll talk about science communication. Okay, so Matt asked, well, what's an example of something which doesn't move as a helix in a magnetic field? So helical paths come from having particles with standard model charges, namely electric charges, right? Okay, what if there are other charges? What if you have, for example, a monopole that doesn't move as a helix in a magnetic field? But, monopoles also don't have a very interesting motion in a magnetic field. They're basically straight lines. But there are other theories. So not quarks, but quirks. Quirks are basically dark sector quarks, but the QCD scale is lower than the mass. And so these are very, very massive particles. And so there's not enough energy to pop new ones out of the vacuum. So you produce two quirks opposite each other. Instead of getting a shower of quirks, they maintain macroscopic distance and they have these crazy oscillations because they have these flux tubes between them. And not an expert in QCD or in quark theory, but I think it's cool that they predict these crazy motions in a detector. Okay, so that's an answer to your question. One example of a potentially viable theory that gives you non-helical motion in a track. Okay, so we said, let's see if we can train this machine learning algorithm to find these non-helical tracks. We generated some quirks, maggraph, et cetera, et cetera. Here's some examples of what they look like. Now, getting quirks into géant turns out to be very complicated because the quirks interact with each other in this strong fashion. And so the technical details are hairy. The lore is that there was a student at Berkeley who spent 3 years trying to get quirks into géant and failed and left the field. So apparently it's difficult. So instead, we just used a simplified detector setup and said, let's have a bunch of cylinders and count where the cylinders, where the tracks intersect the cylinders. We're interested in the core tracking problem. Is this even possible before we get into the details of like DEDX details? So here's a bunch of examples with varying quirk masses and varying confinement scales, capital lambda. And you see you get very different kinds of behaviors. Sometimes you get like this crazy stuff, sometimes bigger oscillations. Sometimes they're just back and forth. Sometimes the oscillations are so tiny you can't even see them. Sometimes the oscillations are really, really big, so you can't see them. But there are a lot of fun ones in the intermediate region where you get really crazy behavior in your detector. And we did two different geometries, one with 8 layers and one with 25 layers to see, was that important? Okay, so this is all work done by Max Feig. He's a UCI theory grad student moving to Fermilab to do a postdoc soon. And Chi Yu Shah, he's a grad student at Beijing working with me. And then Daniel Murnane helped with all the technical stuff on the machine learning tracking. And the way this machine learning tracking works, you don't need to know all of the details, but essentially what it does is try to learn to map all the hits in the detector space into some abstract latent space, where in the latent space, hits that are from the same track should be near each other. So it makes it simpler to search in that latent space. You should find nearby hits just by looking nearby in the latent space. And so then it's able to define these true neighbors and learn to make sets of hits that it thinks come from the same track. And then you identify all the components, stitch them together, and then do the fitting. All right. So I'm going to talk about how well this works. I'm going to talk about efficiency. And efficiency is defined by the reconstructed tracks divided by the reconstructible tracks. And so reconstructible are tracks that leave enough hits for us to find them. And reconstructed means that they're double majority matched to the truth candidate. So majority of the true tracks are on the reconstructed track. The majority of the reconstructed tracks come from that true track. We can get into the nerdy details of that if you like. So first we said, let's do a sanity check. Can we even run this pipeline? Because honestly, it was not easy to get the pipeline to run. So we said, let's give it a bunch of standard model helices. We'll train it on that. Then we'll test it on that and see how well does it do. Okay, it does pretty well. Now this is very simple. Like one track in your detector, can it find it? Yes. Then we said, all right, train that same tracker. Maybe standard model trackers are already good at finding quirks. Maybe this is an easy problem. Take that same tracker, train to find standard model helices, and run it on a sample of quirks. And here we have a benchmark with nice oscillations. How well does it do? Badly. It only finds them when you happen to have mostly a smooth curve. And anytime you get crazy oscillations, it can find quirks. So we can run the pipeline, yay. Quirks are a harder problem. You can't just apply this out of the box. And then we studied the performance as a variation of the mass of the quirks and this lambda, and you see the kind of behavior you expect. If, for example, the tracks are mostly straight lines, you get good behavior, you get high efficiencies, et cetera, et cetera. You can see the details in the paper. All right, so then we said, well, some of these quirks are really crazy. They like go in and out of the detector and leave 1,000 hits. Let's start with the easy problem. We could define them as well-behaved quirks, quirks that leave the number of hits less than 3 times the layers. So you have 25 layers in your detector. These are quirks that leave less than 75 hits. And so, for example, this is the task. Like, take this collection of hits and assign them to 2 sets, one set and another set. Or take this collection of hits and assign them to these 2 sets. Not easy, even by eye, right? Like, these are not nicely separated tracks. They're oscillating around each other. All right, so we tried it. We said, let's give it a bunch of quirks in the training data and ask it to reconstruct them. Can it? Turns out the answer is yes. There's nowhere in this pipeline is there assumption of helical tracks or any kind of assumption which prevents you from learning a new kind of pattern, right? This pipeline is amazing. It's already flexible enough because they've separated the fitting and the finding that it can learn things as weird as quirks. Okay, so I was very excited to see that, but I thought, well, we're kind of on easy mode still, right? Let's do something a little harder. So here's another example of quirks that were found by the pipeline. Cool stuff. And then we studied the performance as a function of PT and as a function of the number of hits. As the number of hits grows past the number of detector layers, it gets harder. All right, so let's try a little bit of a harder problem. Let's add background, right? So far, we just have a single track in the detector. So then we add background. We say, here's quirks mixed in with a bunch of background tracks. And as long as you include the background in your training, say, don't find these, but do find these. So these get a negative label and these get a positive label. Then it does a pretty good job. Obviously, the efficiency is degraded a little bit because it's mixed in with lots of other tracks, but background is manageable. It's possible to find quirks even among background standard model tracks. And then we said, well, what about more layers? Like, does this problem become intractable? And the answer is no. With 25 layers, you got about the same performance as you do with 8 layers. So we're gradually walking our way up to more and more realistic situations. So then we looked at the dependence, the efficiency as a function of all of these parameters, the mass of the quirks, the confinement scale, et cetera. And you see the behavior you expect, that in some cases, the tracks are just straight lines, and so they're easy to reconstruct anyway. Sometimes the two tracks are right on top of each other because the oscillations are so tiny that you can only find one of them because the hits are literally the same. But often you get a pretty good efficiency. But we're not particularly interested in quirks or in one model of quirk. And you wouldn't want to like train a tracking model for one parameter value and then have to retrain it for another parameter value and run like 100 different tracking pipelines just to look for quirks. So we were curious, can this generalize? If you train it on quirk model A, can it learn to find quirk model B? So we did a test where we trained it on standard model quirks, but not the testing sample. So for example, if our testing sample is this set of parameters, then we'll train it on quirks that are not from that parameter set. So other kinds of oscillations. Is it learning to find just the one particular one, or is it somehow generalizing? And we found that the performance is lower than if you train it on what you're looking for, but not devastatingly so. And similarly for this other test point. So it can still generalize a little bit. If you teach it to find a bunch of quirks, it can find a bunch of quirks. You don't need individual quirk pipelines for every parameter value. And then we thought, well, what about the background? What about fake quirks? Because you run this pipeline, it might be easy to have a high efficiency, but what about the purity? If it generates lots of nonsense tracks, then you're also not going to be interested in it. And so we wrote a quirk fitter, which takes the quirk oscillation hypothesis, those red and blue lines, and fits it to the reconstructed points, and calculates a quirk chi-squared. And so as you expect, the quirks do very well, and standard model tracks have a very long tail. So we should be pretty good at filtering out the standard model tracks and reducing the fake rate. Okay, so I think that was exciting. We were able to find non-helical tracks. We have a lot of open questions still. We want to be able to extract quirk parameters from these tracks. I haven't shown you any distributions of how well that behaves. We want to do more realistic tests with more pileup and in JONT and all sorts of details to see if we can find it when the problem is realistic. But we have a first paper out, and you can find it on the archive and describing all of these things. So check that out. So my conclusions from this portion are that the standard model trackers, the ones we have now, cannot find these quirks. Right? However, this machine learning pipeline is pretty agnostic. So it is capable of learning to find these quirks. And it can even generalize a little bit. So now let's talk about other kinds of non-helical tracks, because like quirks are fine. And my colleague Jonathan Feng believes that every reasonable dark sector theory should have quirks in it. But not everybody thinks that's true. So let's talk about more generalized weird stuff, right? Because we're interested in other non-weird, non-quirk stuff, and it'd be wonderful to develop an algorithm which was independent of your theory, which could find any kind of weird track, not just this one example of weird tracks or that one example. What if we found something in the data that looked like this, right? You'd be like, woo, I'm arranging hotels in Sweden now, right? Like there's something there. That's the goal, to find something really weird and unanticipated. So this is work done by my student Levi Condren at UCI. He started to think about like, well, what do we mean by weird? Because you got to have some restrictions. If you have a set of hits in your detector, in principle, you could combine any set of those hits and call it a track, right? That this track teleports over there and then teleports over here. You got to have some limitations. So Levi said, let's limit ourselves to any smooth path. So something with infinite derivatives, right? So we're not going to have kinks or weird stuff. And that rules some things out, but I'd still be very happy to find this in my data. And it turns out there's lots of interesting things which are still smooth paths. Now we have to think about how do we explore the space of all possible weird smooth tracks. Well, that's tricky to think about, But of course, we're tempted to go to Fourier space and think about amplitudes of those Fourier modes. And that's fine. And especially, and this is Levi's insight, it turns out that you can put restrictions on the Fourier amplitudes if you apply this smoothness constraint. That is, in order for tracks to be smooth, they need to have their high frequency amplitudes fall to zero fast enough. And he discovered this set of functions called the Schwartz functions, which probably not named after Matt, probably named after Spaceballs. But what it essentially requires is that you have some relationship between the frequencies that falls to zero fast enough to and will guarantee you this smooth behavior. But if you satisfy that, you can sample from the frequencies below that curve and get smooth paths. But even weird ones, like very, very weird stuff, is included in these Schwartz functions. Okay, so that's cool. We have a definition of weird. We have a way to sample arbitrary weirdness. We've defined this space, and we have some constraints on it, which will guarantee smoothness. I'm not. I assumed it was so that I could make this joke, which could be wrong. Oh, oops. All right, Google it for me. Ask ChatGPT and see if you trust the answer. Okay, so we considered a bunch of different kinds of tracks. We tried tracks with just 2 frequencies in Fourier space, or 3, or 4, or then no limit, just a bunch of frequencies, still limited by the Schwartz function. You see you get lots of weird behavior. This is a plot of the number of hits in a 25-layer tracking volume. This is 160 up here. So sometimes it comes in and out and does all sorts of weird loops, and you get lots of cool stuff in your detector. So Levi said, let me train this pipeline to find these kinds of tracks. So he generated a bunch of different tracks that have 1 frequency. So not a single frequency for the whole training set, but a bunch of individual tracks, each with 1 frequency. And he found that if you train on the standard model and then try to find these, you have very poor efficiency. Same with 2 frequencies, 3 frequencies, all the way up to our full Schwartz tracks. So the problem is hard, right? These tracks we generated are weird enough that the standard pipeline can't find them. But if you train it on these tracks, it can find them. So it's like, hey, I'm happy to find these if you tell me what you're looking for, right? It's defining its latent space in such a way that it allows for these tracks to be considered for these hits to be near each other in latent space so it can find these tracks, even with 4 frequencies or multiple frequencies. The pipeline can learn to find them. And then this is the combination of standard model plus weird tracks. The performances here are like 70 to 80%. And so just like we saw with quirks, but in this case, we didn't have to specify a physical theory. We didn't even have to specify only one kind of path. We have all sorts of different kinds of paths mixed in here, and we're still able to reconstruct all sorts of different kinds of paths, even ones we hadn't explicitly seen in the training sample. So here's some examples of tracks, of Schwartz tracks. Now, one concern is that the Schwartz functions, there's lots of ones that satisfy these constraints, that it falls fast enough in frequency space to guarantee smoothness. Turns out there's an infinite number of those. So if you pick one, you might be using that to define a space, and there could be other weird smooth tracks that are not included in your space. So Levi generated 2 different Schwartz functions, for example, and said, let's train on one and then test on the disjoint tracks, the tracks that are in one but not the other. So for example, if you train on Schwartz space A and test on A, you get pretty good behavior. If you train on A and test on only the ones in B that are not in A, you get pretty good behavior. In fact, the efficiency is slightly higher. And here's some examples of tracks that are in B, but are not in A, but are still reconstructed. They're pretty weird. Okay, so I think this is also an exciting result because it shows us that not only can we find quirks, we can also find other weird stuff that we didn't potentially anticipate. The goal is to construct a training sample that's capable of finding any weird tracks in any part of this space. so that it's broadly powerful. Not just this kind of weirdness or that kind of weirdness, but anything that we consider weird could be found by the detector. Now, Levi has some new results fresh this week. I didn't want to show you, they're too fresh, but he has a paper coming out, we hope, in a few weeks that'll also include analysis of fake rates and with pileup. Okay, so I've shown you that we can find quirks, one specific physical example of non-helical tracks, and that we can probably generalize this to find other kinds of weirdness. Now let's talk about track finding and track anomaly detection. So say we get this pipeline up and running, and it's running on the LHC, and it's spitting out all sorts of tracks. How do we filter out the helices from the non-helices? How do we know that what we're finding is interesting and weird enough? So the classic anomaly detection problem. But it made me think about the connections between tracking and anomaly detection. And there were some connections which I hadn't realized, though maybe you guys had. They seem obvious in hindsight. And that's, for anomaly detection, we often use this kind of structure. You start with your data space, you encode it into some latent space, and then back into the data space. And you train this on your non-anomalies, so it's good at doing this. And then your anomalies, when you feed them in, they don't get mapped back to themselves, and so you have a large difference between the inputs and the outputs. That's your anomaly, right? Okay, so that's the traditional structure for anomaly detection. Let me tell you about tracking using the same kind of language. What we do with tracking is we start from the hit space, and then we do a fit, usually a least squared fit to some parametric model, which maps it effectively to a latent space, the parameter space. So maybe you started with like 10 or 30 space points, and now you have 5 parameters of a helix. This is just like a latent space. Then what do? You take that helix and you map it back into hit space to see, what does it predict? Is its prediction close to where the hits were? If so, this probably was a helix. I've effectively compressed the information from all the hits down to the parameter space, the latent space of parameters, and then back. This works great if it's a helix, and this will fail if it's not a helix. You try to fit something which is a squiggle using a helical fitter, it's going to give you some parameters, but then it's going to predict something which is far from the original data. So to me, this is fascinating. It's very similar in construction to the anomaly detection strategy. Now, typically what tracking is trying to do is trying to minimize the difference between the fit path, this red line, and the hits. So it's looking at these distances in gray, right? It doesn't actually care what the truth was. What was the particle that left these hits, right? It's actually trying to just minimize that difference. But there's problems with this. One is fitting is slow. It's a pain, right? If you are searching a space of parameters for the optimum value, you're searching a 5-dimensional space. You're not doing that by brute force. You have some heuristic algorithm. You've called SciPy optimize. You're doing something. It's slow. It's unreliable. Anytime you're doing a fit, it's pain. Also, this model assumes a Gaussian hit uncertainty. This metric, minimizing the distance between the fit helix and the location of the points, will give you the true track if these hits only have Gaussian noise. So it assumes a Gaussian hit uncertainty, and it actually optimizes for the hit residual, not for the difference between the true track and the fitted track. So I thought, what if we replace this part here with machine learning? Why do a fit, right? This is just a mapping from hit space to parameter space. We can learn this, right? People have done versions of this already with lookup table tracking. This is just a more compact, faster, less memory requiring version of it. So if you learn to map from hit space to parameter space, basically machine learning fitting, then you can avoid the searching of the space. So it's deterministic. You could even run it quickly in a trigger. There's no assumptions anymore of the Gaussian error. You're just learning the mapping. Your hits could have any kind of weird error. It doesn't matter. And you could also optimize directly for the thing you're actually interested in, which is the difference between the true track and the fitted track. So this is what people traditionally optimize for, but what we really care about is this distance, right? We care about the particle. We don't really care how close the track comes to the hits. We care what was the momentum of that electron. So let's optimize for the thing we're actually interested in, right? That's another lesson of machine learning, is that we do best when we optimize for the thing we actually care about. So preliminary results from my student shows, so in red is the neural network, and in blue is the traditional like-signed fit. And these are residuals in two track parameters, so angle and PT. And he finds that the neural network, not only is it zillions of times faster than the fitter, it actually is more accurate in many cases in these track parameters. Not only that, but it doesn't minimize the chi-squared. Like the least squared is searching to minimize the chi-squared. The neural network doesn't care about that. What it cares about is the difference between the track fit and the true track. And so this metric here, this is what I call the truth residual, measures that difference. The neural network is optimizing this at the expense of the chi-squared. So it will return a track with a worse chi-squared, but closer to the true track parameters. So I think that's exciting. This is work by Ryan Miller at UCI. And this makes me wonder, is it possible to somehow use this with a weird track finder to map this hit space into some weird track space, maybe Fourier modes, I don't know. But you certainly can't use helical parameters there. And then map back and use that as some sort of anomaly detection. Okay, so for the science portion, my conclusion is that these machine learning tracking pipelines are amazing. I don't take any credit for them because I didn't develop them at all. But identified this tool is capable of separating the fitting and the finding, which allows us to learn non-helical tracks as just a bonus. Even broad, weird classes of non-helical tracks. And I hope this means that we can develop this into an actual tool we can run on our data and maybe find some stuff. Maybe there's something out there in the data waiting for us to uncover it that we have long ignored because we assumed that this kind of stuff was impossible, behind a wall that was intractable. But machine learning is making what once was intractable, tractable again. Okay, so I briefly want to change topics completely. I've been doing science communication for a lot of years, and for a long time, I never talked about science communication at research talks because I wanted to make sure people took me seriously as a scientist. And somebody recently convinced me that was a mistake, and that instead I should be normalizing science communication. So I want to take 5 minutes to tell you about my science communication, which is a passion of mine. So I write popular books. There's one called We Have No Idea, another one, Frequently Asked Questions About the Universe. Coming out later this fall is a book called Do Aliens Speak Physics? About when aliens come, can we talk to them about physics? Or is our physics more human than some theorists anticipate? I have a couple of podcasts and a TV show. So you might ask, well, Daniel, you seem like a busy guy already. Why are you doing science communication? And the answer is, we need people out there speaking the truth because there's a lot of folks out there talking nonsense. If you look on Twitter, there's people out there saying like Big Bang Theory is nonsense. Everything you've been taught about the world, how the world works, is a lie. Like, it's a big step to try to tackle this stuff, but I think it's worthwhile. Even high-profile coverage of our field sometimes makes me cringe. Like the Higgs discovery was described as having revealed the deepest layer of reality our species has ever probed, dude. Like, I don't know what Dennis Overby was smoking when he wrote that, but I don't even know what that means, And more broadly, I think science communication needs some attention. Like, there are folks out there, doctors even, who don't seem to understand the difference between correlation and causation, right? Like, yes, there may be a correlation between how much coffee you drink and your lifetime. Doesn't necessarily mean you should be drinking more coffee, right? It's an old problem. It's a standard problem, right? Something we need to teach people. If correlation and causation were connected, then we should really be going after Bill Gates for all these murders. And sometimes you find the best science communication, in the places you least expected it. Like this one actually gets the correlation correct, which I respect. All right, so a couple of years ago, I did a video comic with a friend of mine, Jorge Cham. He's the guy behind PhD Comics. I'm sure I saw a bunch of his comics up on doors here. Everybody knows his work. And he's a really nice science communicator. We talked about the Higgs boson and what it means. And That was a lot of fun. We put it out just before the Higgs discovery, so it ended up being picked up by popular media. It was all over the place. It was nice. It was a lot of fun. All right. And one of my most proud moments, though, was when they announced the Nobel Prize for the Higgs boson. Of course, it's not named in the discovery because of my tiny role in it. However, in the further reading section of the citation for the Nobel Prize, they did link to our comic. So I don't have a Nobel Prize, but I've been cited by the Nobel Committee, which, yes, I have put that on my CV. All right. And then we wrote a book in 2017 called We Have No Idea. It's about all the things we don't know about the universe instead of all the things we have figured out. And the approach here was to be very accessible, to admit the things that science has not figured out, and to do so with some humor. And I worked with Jorge on these figures to try to make them accessible. And the idea of using cartoons is to give people the sense of, hey, these are weighty topics, but you can understand them. And so, we made silly jokes along the way to keep people entertained. The book was translated into like 30 different languages. I have no idea if the jokes translate or not. I don't read Hungarian or Turkish or Chinese. I hope so. What's that? Yeah, Jorge and I wrote the book together. I wrote the text and Jorge did all the cartoons. Then we came out with another book, 2020, Frequently Asked Questions About the Universe. And when you put stuff out there, you got to sometimes look at the comments, and sometimes they're wonderful. Like, we put this book out, and here's a review that says, I laughed throughout the entire book. My kind of humor. Oh man, it's nice when you do something and people get it. Like, okay, they get it. And then there's the other side of it. Like, here's a guy who wrote a very long review. This is a small portion of it. And his main complaint is that we said these problems were unsolved, but he knows the answers. And why didn't we talk about his theories? All right. Here's another guy who said, dial back the dad jokes. I'm like, sorry, I'm just not capable of doing that. So if that's what you want, go somewhere else. Or somebody who gave us a 1-star review on the book. I was like, what, 1 star? It's because it was left on his doorstep in the pouring rain. And so I got a 1-star review. Not fair, man. Anyway, then we started a podcast. Daniel and Jorge explain the universe. We talk about all kinds of stuff in physics in an accessible way, make jokes along the way. Recently, I started a podcast with Kelly Weinersmith. Her husband, Zach Weinersmith, is the guy behind SMBC Comics. And together, they recently wrote this book, A City on Mars, about whether we're ready to colonize Mars or not. It's a really good book. I encourage you to check it out. And so this is our podcast, The Extraordinary Universe. It's a lot of fun. And on the podcast, I tell people, if you write to me with a physics question, I will answer you. And I do. I answer every email from listeners. I get lots of them. They come in every day. They're interesting. I do answer every single one. This one, I actually wrote to this guy's mom and asked her if I should answer this guy's email or not. He was 10 years old, and I thought, I don't know if I should be creating the next generation of supervillains. But it's fun interacting with people. I think it would be quite dangerous. I don't think it would destroy the Earth, but it could make it impossible to live on Earth. And so the podcast was quite popular. We're often in the top 3 or 5 in Apple Podcasts for natural sciences. What Apple Podcast calls a natural science podcast, though? Like, we're behind the Sasquatch Chronicles and Brett Weinstein's COVID misinformation podcast. Like, don't know what that says about Americans, but I know that in the UK, they know something more about science. So in Great Britain, we're number 1. No, there's many. And we got lots of great feedback on the podcast. Here's a woman who listened to our podcast and at 60 went back to get a university degree in astronomy. And I thought, well, that's nice. We like really reached somebody, touched on the passion they've always had in their life. Here's a guy who likes to listen to the podcast because my voice puts him to sleep every night reliably. And I'm like, as long as you're downloading it, I'm fine. Here's a guy who listens to the podcast because it drives his wife crazy on long drives. And I don't want to be responsible for this guy's marital therapy, but as long as he's downloading it. So my latest project is this book, Do Aliens Speak Physics? It's with another cartoonist and a friend of mine, Andy Warner. I found that a lot of folks in physics assume that, when aliens come, we can like go to the chalkboard and start writing Lagrangians and it'll all make sense, dot, 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 dot. But if you talk to philosophers and linguists and anthropologists, they're deeply skeptical about the plausibility of that. Or if you look at, for example, Carl Sagan's, Voyager plaque, the stuff he sent out there, like the odds of some alien civilization looking at that and understanding it seem minuscule. So I thought it would be interesting to examine this, like, what do we know about how universal is our science? What can we say about that? So this is a fun book. It's coming out later this fall. And then a few years ago, PBS put out a call for a new educational television show, a broad call. They wanted new people who were not in the PBS family. So Jorge and I put together a pitch for a show. And I did a bunch of reading about in educational journals about how 3 and 4-year-olds learn science. It turns out a lot of 4-year-olds aren't taught any science because people at that age, teachers at that age, are afraid to talk about science with their 4-year-olds because they're afraid they will be asked a question they don't know the answer to. And so our goal with this show was to model kids being curious and asking questions, but then the adults in the show don't have the answers. Instead, they work with the kids. They say, I don't know, how will we figure it out? So the show doesn't teach kids science, it teaches them how to answer their own questions. And my hope is that the adults who are like listening in the background while they're making dinner will also learn, hey, it's okay to say, I don't know to your kid. We can still talk about science. So that was the goal. PBS liked the idea and they said, all right, make it. And my response was like, what? How do you do that? I could come up with an idea for a show, but like seriously, how do you make a television show? I didn't know where to start. But we learned, we visited a bunch of studios. I got to go to the Jim Henson studios in LA and like see the original Dark Crystal Muppets. Amazing. Learned special software for writing scripts for television. It was crazy. Then we tested one. So we wrote this episode, we made the pilot, and I literally stood behind a one-way mirror as 4-year-olds were watching it. And PBS executives were like, did they laugh at that joke or not? But the 4-year-olds gave us positive reviews. PBS said, great, make us a bunch more. Turns out when you sell a season of PBS, they want 80 episodes of your show. Blew my mind. And they don't pay for it. So this is like a $25 million project. They paid for 10 million. And they're like, now you go out and find the rest of the money. I said, oh, okay, great. Let me call up all the eccentric zillionaires I know. So we found some funding from the Corporation for Public Broadcast and from Department of Education, both of which now have uncertain futures. And season premiered in 2020, and we got some very nice responses to it. Season 2 is now wrapping production. The future of public television is uncertain, but it's been a lot of fun. So why do science communication on top of everything else? Because it's important. Somebody needs to do it. I think it's important that we have scientists participating in these conversations. And also, it's fun. This is a lot of fun. It's a break from the other kinds of things we work on. And there's a lot of people out there who are really excited to hear from us. All right. Thanks very much for your attention.
All right, thanks, Daniel, for a wonderful presentation. We take questions now. Are there questions in the room or online?
Matt, how do you spell Schwartz correctly? I was correct with a T. I should have pretended to know that. I should have bluffed my way through it.
So I have a question about this Fourier fitting thing, So I'm a little confused how you do this. Like, couldn't you fit every single hit in the detector with like one really, really big weird trap? And how do you separate normal traps from weird traps in the same event?
Yeah, cool. So you need to have a smooth differential path, which prevents you from fitting every single hit. You can't always draw a smooth path for every single hit in the detector, right? That's the difference. You're right that if you just say any track at all with no limits, then you could connect the dots to do anything. But if you require smoothness, then you can't.
But even this one here, that looks smooth, and that looks like you can fit it maybe every single hit in a like,
But I mean, like you certainly can't fit every single hit. I mean, you're being extreme when you say every single hit, surely. You're worried about fitting all sorts of crazy hits, right? Yeah, and so that's definitely something we're working on. And as I said, I have some results on that, but they're tentative. So like fitting together random sets of hits and calling them a weird track is definitely a concern.
how do you separate, like, you can fit, maybe if you have like 10 hits in a row, you can fit it in a straight line, or you can fit a crazy function through it with extraneous bumps in it. How do you tell the difference?
I mean, I think in that case, you'd want the simpler explanation, right? So the fewer Fourier modes you need, definitely the best. Yeah, but they're good questions.
I guess just kind of a follow-up on that. Do you include penalty terms for the complexity of the thing that you're fitting, or weight it towards low versus high frequency?
Not yet, but definitely something we're thinking about. And I think that's going to be part of the sort of anomaly detection section of it. Like, when do you consider it? What are you looking for, and how do you weight these things?
I also still don't understand the answer to your question. I mean, you could just put a spline through any point, right, and make a smooth function, arbitrary order, arbitrary polynomial. Like, what are the rules? Like, is there some physics that motivates the types of curves you're looking for, or how do you get at these force functions, or what's the principle? Is this something aliens would come up with? Is their physics?
I mean,
Motivating.
it's true for an arbitrary number of hits, you could fit a polynomial of degree n. With n hits, you could fit a polynomial of degree n through it, right? So we're definitely looking for something simpler than that. And so that's why, for example, we start with 2, 3, 4 Fourier modes. So we definitely would prefer fewer modes in the track. Is that what you're asking? Or are you asking, how is it
Yeah, but
possible?
what are the rules, I guess?
Yeah, we're still figuring that out. So this is still a work in progress.
For example, a helix doesn't the most minimal description of the track, right? Would you have come up with a helix?
A helix is the most minimal description of a track that actually is moving in a helix, isn't it?
I don't know.
5 parameters. I think it's pretty compact.
I mean, but if you did the Fourier analysis of the helix, would it have? Decomposing on a different basis, right?
Yeah.
So if you did a Fourier analysis of the helix, would it?
Yeah.
I
Well, that's a cool
probably it has
question.
very few frequencies because the helix, but in general, I don't see immediately why your criteria for simplicity is the same as the one nature would prefer.
Yeah, I can't guarantee that it is. It's an interesting question. Like, could you fit how many modes would it take, or where in that Fourier space would a helix land? Essentially, is what you're asking. But I think there's a deeper question there, which is like, how do you limit the complexity of the things you're considering, right? And so that's not something we yet have the answer to, and I think that's going to come out in the anomaly detection section. First, we want to make sure, can we find these things, and then we want to filter out the craziest explanations and the noise. But first step is just like, can we find them at all? But definitely important question.
Any more questions from the room? Or is there anything online? I have one question as well. So I think if I understood it correctly, okay. Well, can you just quickly ask my question with that? Yeah. So, so if I understood it correctly, the whole training setup for finding weird tracks is sort of supervised. So you give these like classes of different smoothly imposed weird tracks, and you try it, and you label them. Have you tried anything unsupervised or semi-supervised or something?
No, not yet. No, on the list.
Okay.
But yeah, so far fully supervised.
Can you read it from which? Oh yeah, if from online you can unmute, because I don't know if it's written in the chat. Yeah. Please go ahead.
Oh, yeah. I was wondering if there were some geometric properties in those paths of interest, right? The weird paths that could be exploited to help a model find them. Because I have seen that certain graph neural networks are designed to be equivariant for things like rotations or translations. So you could maybe in the design of the graph neural network, think about those symmetries from the paths to help it find those paths of interest.
Yeah, that's a cool comment. Thank you. It's certainly true that some of those symmetries will be present here, right? You don't care about the phi rotation, for example, if your detector is symmetric in phi. So you shouldn't learn a different tracking in every direction. So yeah, definitely taking advantage of some of that could be helpful. Thanks for the comment.
All right. Any more questions online? If not, I think we can test once more Daniel for the wonderful presentation. And as usual, we go upstairs and we keep on chatting and connecting all together in the penthouse. Thanks.